My name is Josh Craver, and I'm an assistant professor of controlled environment horticulture at Colorado State University. Today I'll be covering some basics regarding CO2 enrichment in controlled environments. Specifically, I'll cover why CO2 enrichment may be beneficial to optimize production, as well as some strategies that may be used to ensure appropriate CO2 concentrations in your controlled environment. So let's start with why we should consider using CO2 enrichment. Now, generally, it's been found that plants respond favorably to elevated CO2 concentrations in terms of photosynthesis and growth. Now, there have been many documented benefits to CO2 enrichment throughout crop production, including increases to biomass and yield, increasing crop quality, earlier flowering, improved water use efficiency, and improved light use efficiency. Now, this favorable response in terms of photosynthesis makes sense. Specifically, if we look at the equation below, we can see that photosynthesis requires inputs of carbon dioxide, water, as well as energy from light, and that ultimately gives us the products of sugar and oxygen. Now, our focus in controlled environments is often on the light environment, and it can become easy to forget that just like light, CO2 can become equally limiting to photosynthesis. Now, for many species, we generally find that photosynthesis increases up to a maximum CO2 concentration of 800 to 1200 parts per million. Now, it's important to remember that our ambient CO2 concentration outdoors is approximately 415 parts per million. So for controlled environment production, we're often looking at recommendations of 2 to 3 times our ambient concentration outdoors. Now, enriching beyond this recommended range can be wasteful. Specifically, CO2 is often no longer the limiting factor for photosynthesis and growth. In other words, we can continue to increase the CO2 concentration above this recommended range, but it likely won't result in further increases to photosynthesis as the plant has reached what we refer to as a point of saturation. However, one of the greatest limitations to photosynthesis and growth occurs when CO2 concentrations fall below the ambient concentration outdoors. Now, a great example of this can be observed with greenhouse production during the winter months on a clear, sunny day. Specifically, the clear, sunny conditions in the greenhouse will ensure our crop has adequate light for photosynthesis, which we would all generally consider to be a good thing. However, during the winter months, we're often limiting ventilation in the greenhouse to conserve heat. So by limiting ventilation, we are in turn limiting our capacity to replenish the CO2 concentration in the greenhouse. In short, we have a scenario where our crop depletes the CO2 available in the greenhouse due to the high light conditions, and that CO2 is not adequately replenished due to the limited ventilation. For a well-lit, closed greenhouse, the CO2 concentration can actually drop below 200 parts per million with a full crop canopy. Now, in this scenario, it's critical to remember that light is not our limiting input for growth and photosynthesis. CO2 is. So as a result, supplemental lighting provided during conditions where CO2 is limited in the greenhouse results in very limited to no benefit to the crop and is potentially just wasting energy. This provides a perfect opportunity to consider CO2 enrichment to alleviate this limitation on photosynthesis and growth. Now, if you remember from a few slides back, a common target for enrichment in controlled environments is 800 to 1200 parts per million, or 2 to 3 times our ambient concentration outdoors. There are many technologies we can utilize to provide CO2 enrichment, including CO2 burners and compressed or liquid CO2 tanks. Now, simply increasing your air exchange rate may also be a cost-effective way to ensure that close to ambient CO2 concentrations are achieved without investing in other enrichment technologies. However, you must be aware of how this will impact your environment, especially in terms of heating during the winter months. Lastly, improving air movement through proper placement and sizing of fans can be another excellent way to ensure that CO2 concentrations are replenished within these dense crop canopies. Thank you all so much for watching, and I would specifically like to thank the USDA's Specialty Crop Research Initiative for funding and supporting this project.